All right, today we're going to try and talk about how we calculate a magnetic field around a current carrying wire. And this is very much in line with trying to figure out the electric field around a infinitely charged wire. It's going to be a very similar feel to it. It's definitely going to be a sum, and it's certainly going to require an integral. So from now on, when there's something that requires integration, I'm going to be, or at least try to emphasize this is something where you are going to have to use integration to solve your problem. Now, I said to you yesterday that although all of those things are true, there is certainly an easier way to do what we were about to do, just like there was an easier way to do it when we talked about the electric field using Gauss's law. There is an easier way to do this using Ampere's law. But if you think back to when we talked about Gauss's law on its own wasn't exactly easy to understand in the beginning. I'm not sure if I asked you guys to use Gauss's law now that I would have 100% success. I might have some success, but I'm not sure if I'd be hitting 100%. So Ampere's law, which we will learn next week, will do the problem we're about to do in a few short steps. But just like Gauss's law, Ampere's law also requires integration. But if you remember, with Gauss's law, the goal was to try not to integrate, was to try and set up the problem where the integrals ended up being of constant values. Same will be true for Ampere's law. We're going to try not to integrate. But when we're using Biot Savarte, there's really no choice. So Biot Savarte is a sum. We're going to be adding up every contribution to the magnetic field from an infinitely long wire. So I'm going to start by saying we have an infinitely long wire that is got a current I. Now, as you guys attempt to take notes, if you are trying to write down notes that will give you some sense of hope when it comes to understanding this, because I've looked at some notes over the last week and a half, one thing you want to understand is this, like an electric field, is spatially based. We're going to try and come up with the magnetic field in some location in space. So we are picking a place. And we're hopeful, this is something too that I want you to know, that our expression will allow us to apply it to all sorts of places in space. So we're not just interested in this one location, but we might be interested in all locations around the wire. We're just using this one location as a means of doing a single sum with the hope that we'll use placeholders here, variables that have some kind of meaning that we could then say, well, because of symmetrical relationships here, perhaps the answer for this location in space will also be useful for this location in space because of certain amounts of symmetry. But we also are probably going to dictate a few other little minor inconveniences, like this works great if you're up close to the wire. But if you start getting further away and your wire isn't really infinite, maybe it doesn't work anymore. So we're going to base it on an infinitely long wire, but there are no infinitely long wires. There are wires that are really long when you're very close to them. You follow what I'm saying? So there's a certain amount of understanding that we're saying infinite, but in the microscopic world like this, infinity isn't that far away. So we're going to try and make a bunch of placeholders to describe the magnetic field a distance away from the wire. And let's go ahead and define this location as being a perpendicular distance z away from the wire. As that is a pretty traditional variable about this thing. And this is our location in space. We'll say it's right there. All right. Biot Savarte tells us the contribution to the magnetic field from a piece of the wire. So when we start writing out the Biot Savarte law, we have a contribution to the magnetic field, a single amount of magnetic field. That's what dB represents. And that equals, we have a constant of proportionality. So this is just something out front. It's like K for Coulomb's law. It's a constant of proportionality. Very interesting. So there are parts to this. Pay attention to the parts. So the next part, and the part that, and you will be disappointed in me, but I do have to do this with some notes because there's a lot happening here. The top of this is I, D, S. S is a traditional letter for a piece of length of the wire, but you could use X or Y or anything you want here, even L. L's hard to use because in italics in a textbook, it blends in too much. So it's often S, especially since sometimes our wire is bent in an arc, and since S is a traditional letter used for arc length, S is often used here. But it is a vector portion, right? It points in a direction. And in the case of the way this is supposed to work, since current isn't considered a vector, this points in the direction of current flow. Does that make sense? All right. Cross R hat, where R hat represents the direction from this piece of wire to our location in space. It just conveys direction. It does not convey any amount of size. And that's because the actual reference for size is in the denominator, indicating that the further away from the wire you get, the smaller the contribution to the magnetic field. It's an inverse square law, just like Coulomb's law. So there's a lot to unpack here. So let's choose a place along the wire. And I'm going to choose 2 places so we can be demonstrative of the curl rule. I'm sorry, demonstrative of the right-hand rule. I'm going to pick a place over here. I'm going to say this is a piece of wire. And I'm going to pick a place over here and say it is a piece of wire. I'm only going to set the problem up for one of them, but I want you to prove to yourself using the right-hand rule that both of these pieces contribute in the same direction to the magnetic field. So in order to do that, I would encourage you to draw something for R and maybe draw a temporary one over here, but we're only going to use one of these in our actual calculation. So if this is DS1, this is DS2. That's our value for R. Now remember, R hat is a unit vector that's just in the direction of the value for R. So right-hand rule, our first vector in the cross product is the piece of wire in the direction of current. So for both of them, that's going to be this way. It doesn't matter where R is. Okay, that's an important detail. R is always going to have a component that is beneath the wire in this drawing. Would you guys agree? So whether we're talking about this point here where I line my fingers like that, they still define a plane that's in the board, but in the definition of that plane, my thumb goes into the board. And similarly over here, doesn't matter that DS is in this direction and R kind of has to bend backwards a bit, as long as my component for R is on this side of the current. All of my contributions to the magnetic field are going to be into the board. That's why I told you for a current carrying wire in a magnetic field, you could use the curl rule. Put your thumb in the direction of the current and your fingers will curl in the direction of the magnetic field. Because there's magnetic field over here too and up there. We've picked a single spot, but our goal is to try and understand what the shape of the magnetic field looks like. And it is going to be circular around this wire. Because if you had a spot hanging in space right here and you tried to use the right-hand rule, you'd notice it's going to look something like that. If the spot is out here in space and this is our current. So we get a circular magnetic field around the outside of our current carrying wire. But all of these pieces of wire contribute to a magnetic field that is in the same direction. And that's going to be into the page. Now, I am going to get rid of this because we only need to study one of these. So we'll study just one of them. And now that we have handled that the magnetic field is into the board here, we have taken care of the the cross product. I would handle the cross product first, because once you've handled the cross product, our expression can immediately change to something a little bit more palatable because it no longer has the vector portions in it. So now it's I ds over r squared. Once the cross product goes away, I can get rid of that. But I do need to add something. The cross product went away, but if you recall, the cross product, the value, the size of the contribution is related to the angle that is between R and ds. So that's going to be this angle. So we'll get maximum contribution when we're right here, but we only get partial contribution where we're anywhere off of that point. Right? Sine is a maximum at 90. Everybody good? All right. Now, when I look at this, and I hope you're seeing it too, this part's still a constant. This part is also a constant. A current carrying wire carrying a current, the current itself is constant. So none of those contribute directly to the integral portion. They're going to contribute to the answer, but they don't contribute to the integral portion of our answer. You guys follow what I'm saying? So when it comes to actually taking the integral, the only things that are going to matter is the size of my piece of current, the angle that R makes with that piece of current, and how far away we are. Now, as we've talked about before, in situations like this, every single ds is going to have a different R and a different angle. We're going to need to find a way to express everything in terms of the angle or everything in terms of R. And we're going to also have to find a way of expressing ds. So, it doesn't make much of a difference to me, but let's start looking at how these things might be related. I'm going to notice that there's a right triangle there. Are you noticing it too? In noticing the right triangle there, I'm noticing that for the most part, regardless of where ds happens to be, the triangle is always going to have z as a component of part of that right triangle. Z, therefore, is going to be a constant. It's not going to change regardless of where ds is. It would be nice to work that constant in, because I think you would all agree that it's very likely that the magnetic field is going to be related to z. Does that make sense? So as we try to construct our integral, we want to start looking at things I think are probably going to be in the answer, and I'm pretty sure how far away from the wire we are is something that's going to be in the answer. And since it will be the same for every ds and every angle, it would be really nice to have z in there, because it's probably going to make our problem work out a little bit easier. So I'll notice that the sine of our angle happens to be z over r. Would you agree with that statement? Now, this gives us a way of replacing either r or z. It's a choice we have. Now, as we make this choice, one of the things I would try to consider is, do we know things about this that will be easier to work with? For example, I don't know that I know the limits on r. Like if I put it all in terms of r, how is s related to r? I'm pretty sure r is going to go from one infinity to another. Right? R is going to be an infinitely long distance, and then eventually it'll get small, it'll be z, and then it'll be an infinitely long distance in the other direction. So that's one thing I could do. I could also consider that this length is more closely related to ds. I could identify this as a length s, and maybe write this as, I don't know, tan phi equals z over s. But then I lose r, and I need to find a way to replace r. These are all decisions I'm trying to make. And ultimately, I have to also decide, do I want to do this in terms of r, or maybe I want to do it in terms of s, or do it in terms of the angle? I'm going to choose today to do this in terms of the angle, because I think the angle goes from 0 to 180 degrees. Do you guys see what I'm kind of conveying there? because when S goes to infinity on the left, this angle goes to 0. Would you guys agree with that? Okay. And of course, when S goes to infinity on the right, and we're over here someplace, this angle goes to 180 degrees or pi. Do you guys see that too? Because that has to be the angle we use. We pick one angle, we stick with it. So I can see this sweeping across. I'm pretty sure I'm going to use that angle. Is that all good? All right. So let's consider that I think it might be best for us to do this in terms of the angle. All right? So I have a way of replacing R in terms of the angle. And I have a way of considering ds in terms of the angle. But this is going to require your help. Because if I want ds, I'm going to have to take the derivative of s with respect to the angle. You guys see what I'm suggesting here? You guys have taken calculus now, and you're far enough along where if I want to replace ds, there's ways to do it, but I want s in terms of the angle. And I have a relationship between s and the angle. So if I take this derivative with respect to the angle, I should get something I can replace ds with that's in terms of the angle. This is where I said I need your help, because you should be able to do this one. Right, you've done all the trig functions in calculus now, right? You've done all the derivatives of the trig functions now. Z is a constant. So I'm going to be patient, but I would like you to take this derivative and work it out for me. Now you can do it either way. You could do it tan phi equals z over s and take the derivative of tan phi with respect to s, or you can solve it for s and do it this way. But I need you to do this part. Okay? So I'll give you a moment or two. So going back over here and recognizing that we're trying to assemble this, let's begin replacing things here. So starting with pulling all of our constants away, I have ds, which I'm going to replace with what we just found out, negative z over sine squared phi. So that's ds only being replaced. I forgot the d phi, so let me put that in there. There. So there, all I've done is replace ds. I still have to replace r squared. So I'm going to look over here, and that's r squared, isn't it? You guys see what I'm replacing? So it's going to go on the denominator. So can I just flip that and put it over here? So I'll have sine phi over z quantity squared. I flipped it because it's in the denominator. Is that all okay with you? I thought it would look neater that way and less cumbersome. But I'm trying to make sure. So this represents our 1 over r squared, and this represents ds. Just trying to make sure all of our pieces make it in there. Now, the only thing left is we haven't accounted for the other sine phi that happens to be there. We need to account for it too. So now we have all the pieces in place. This was already there. All I did was take this and bring it over. Now, I don't know about you, but I see some things that we can reduce here. Do you? Yeah. For example, there's a sine squared and a sine squared. Let's get rid of those. And I have a z squared in the denominator and a z in the numerator. So let's go ahead and rewrite this again. I do have this negative sign. We'll get to that. And I'll have z over 1 times 1 over z squared times sine phi. All right. I think we're doing okay now. Any questions yet? Yeah. This sine squared and this sine squared canceled. But there's still the other sign left over. So we had lots of signs. Yeah.
Where did the dp go?
Oh, I haven't written it in there yet. Sorry. There. So I think we've assembled the whole thing. Now, I'm going to recognize that z is a constant. You guys good for that? Right, z doesn't change. And I'm also going to recognize that I can cancel one at the top with one in the bottom. So I'm going to write this one more time with all the constants collected. So I'll have mu naught I over 4 pi z times sine phi d phi, and I still have this negative sign. I think we're good to go now. Now, it's hard for me to express this because I find this to be incredibly complicated and difficult. And I've done this a couple of times myself. And of course, once you get Ampere's law, you probably won't do this again. But you tend to think that the complicated stuff is the trig. I'm sorry, the calculus. But we haven't done any calculus yet, except for taking one derivative, right? Everything else has just been algebra and trigonometry. I think that's the hardest part. Assembling the integral is really, really hard to do. And we had to know, okay, am I going to replace phi, or am I going to replace s, or am I going to replace... We had to know these things. I chose to do the whole thing in terms of phi. We could have done the whole thing in terms of s and gotten rid of phi. And we probably would have gotten a similar integral that would be something we would have to go from negative infinity to positive infinity. Right now, we have an integral here that we're going to use to add up all the contributions to the magnetic field. But this portion is devoid of the problem, meaning it is separate from the current carrying wire. This is just doing the calculus part. We want to add this all up to get the entire magnetic field. And I'm going to put the integral sign on the sign apart from the constants, because none of those change as we add all of this up. Sean, you okay? All right. Now, do you remember we set some limits on theta already? Do you remember those? Yeah, 0 to pi. Bless you. All righty. We ready to go? Now, we're going to have a problem going from 0 to pi. Do you know what the problem is? Well, we have a sine function. If we do this correctly, I want to make sure we could go from pi over 2 to pi and double the answer. Remember that? These are things to think about. So when you're looking at this problem and trying to figure out what to do here, I know that when we take the antiderivative of sine, we're going to get cosine. And cosine of 0 isn't 0, it's 1. You follow what I'm saying? If this had been a cosine function instead of a sine function, then our antiderivative would have given us sine, and we would get 0 minus 0 as our answer. That's probably not the reality. When you're looking at this, part of the reason why you might break this up into doing just a half of the integral at a time is to be looking at the future of what happens when you integrate. Are you guys following that argument, or did I lose you? You are? I lost you? Okay. What is sine of 0? What is sine of pi? If this had not been sine, but had been through whatever happened in our derivation, had been cosine, we know there's a magnetic field there. It's very unlikely to be 0. But the antiderivative of cosine would have produced a sine, right? And well, do you know what the antiderivative of cosine is? Well, what's the derivative of sine? So the antiderivative of cosine is sine. Okay. So that does explain some of that. But when we would take the antiderivative of cosine, we'd get sine. And in this case, we'd have to plug in 0 and pi, which would give us 0 minus 0. We know that's probably not likely to be the answer. Looking at the future, we might have said, well, instead of going from 0 to pi, maybe we double it and go from the halfway point to pi. Does that make sense? We've done this in the past with other questions too. I'm just having you try and think about the future of what's going to happen. In this problem, though, we didn't have cosine. We had sine here. And what is the antiderivative of sine? It's negative cosine. Well, cosine's going to work out okay. So I think we'll be okay putting in cosine here. But you look for these kinds of possible future issues. So B equals negative mu naught I over 4 pi z times, all right, negative cosine phi evaluated from 0 to pi. Can I just bring that negative sign out and cancel it here? You guys all okay with that? It's a constant, it's just a negative 1. And then mu naught I over 4 pi z times, what is the cosine of pi? Minus, what is the cosine of 0? All right. We're almost there, right? So I just see negative 2. Do you guys see that okay? All righty. The negative seems troublesome. It's a holdover of the cross product indicating the direction of the answer, which we already know is into the board. So we don't need the negative sign. It was just giving us, again, a holdover about the direction. If you remember, the original sign was there because of the cross product. You guys follow what I'm saying? The whole way back here, this cross product produced that sign. It is that thing that contributes to this negative sign. We can ignore it. I'm not saying to throw away negative signs. I'm saying to consider them. Now, folks, I was deliberate and very slow today. Would you agree? That was purposeful so we would understand all the pieces. Let me be very frank. If you take away anything today, please commit this to memory. The size of the magnetic field around a current carrying wire. And I mean like put it on a note card, study it tonight, have it committed to memory tomorrow. In this derivative, the z is a constant. The left side is just ds d phi. The right side, the z passes out, and I'm looking for the derivative of 1 over tan theta. Or I'm sorry, tan phi. Now, this is the derivative of cotangent. And some of you, just memorized it. Some of you are trying to work it out. If you're trying to work it out, you can. You probably have to break this up into cosine over sine and do the quotient rule. Do you remember the quotient rule? You could also break it up into cosine times cosecant and do the product rule. You'd have to know you'd have to know the derivative of cosecant. It doesn't matter which one of these you do for me, but you should have this one. Now, there is a direct answer, and trust me if I say if you don't remember this, it's okay. If it ever shows up on the AP exam, the derivative of 1 over tangent phi will be on the equation sheet. So any year that they put it on there, they'd have it for you. But who can tell me it? Because I got like 8 people out there who've got it for sure. Go ahead, Gage.
Negative z cosine theta squared.
Cosine theta squared? Cosecant squared, right? It's cosecant squared, isn't it?
Yeah.
Yeah, so it does produce a negative sign. That's not uncommon. But it's cosecant squared. I'm going to write it as 1 over sine as opposed to writing it as cosecant. And I'm going to multiply both sides by d phi because we're going to use this as a replacement for ds. So there's alternate ways to try and figure out how to replace a derivative. When we have a function, the best way to do so is by using the function to make the replacement by taking the derivative of the function. But this gives us our replacement now for ds.